Hello students, welcome back. The final topic here is section 4, L'Hopital's rule. L'Hopital's rule is a limit computation technique, so some people may think this is a bit out of place, but believe me, it is related to linear approximation. Here's the statement. We have fractions, so it's a bit hard to read. Let's go with a little bit bigger font. Okay, here we go. It works for 0 over 0 type limit. Please note that we have u of c and v of c are both 0. So if you have 0 over 0 there, if you plug in x equal to c, in that case, we can take the derivatives like this. And of course, by taking derivatives, if you get simpler limit, then you can do your computation from this point on. If it is not simple enough, but still 0 over 0 type, then we may have to do this again. Another derivative. In some case, however, even though L'Hopital's rule is true, this limit obtained by taking the derivatives are even worse than before. In that case, you have to stop. You have to find some other method that works. That's going to be typically the case for many of the infinity over infinity type limits. So, L'Hopital's rule works for infinity over infinity type limits, theoretically, but in practice, maybe not, because the resulting limit is even worse than before in many cases. Of course, in some cases, it works out okay. We're going to talk about those, but let's talk about the theory just a little bit. Why do we deal with this along with linear approximation? That's because it is related to linear approximation. You see, u over v can be written in terms of linear approximation like this, and u of c here and v of c are both 0. So drop those, and then we get this expression, and then x minus c, they are common, so drop those, and we get, we just get u prime of c over v prime of c. So indeed, we get what you want. Okay, so much for L'Hopital's rule in terms of theory. Now let's talk about actual application. Here's the first problem. Do you all recognize this problem? We went through the very same example in lesson 2, and that was actually a pretty easy problem. Here we go. Factor the numerator and factor the denominator, and you can see that x minus 2 is common. Cross those out, and what's left is no longer 0 over 0 type limit, so plug in the numbers and do your computation, and you have the answer. Pretty simple, isn't it? But using L'Hopital's rule, you can get equally a simple answer. Here, it's 0 over 0 type limit, so take the derivatives. And then you can plug in x equal to 2 to both numerator and denominator, because that's no longer 0 over 0 type limit. And then do your computation, you get the answer anyway. Now, which is easier? To me, it's a kind of push, about the same. Maybe a slight edge over L'Hopital's rule. How about this now? This is going to be far more challenging factorization because we have non-monic trinomials, but also look at these numbers. They're huge. So factorization is much tougher. It's possible, but it's tedious. Indeed, if we factor, we get something like this, and 3x minus 2 is common. No, this and that. So cross those out, and what's left is no longer 0 over 0 type limit. So plug in the numbers and do your computation. Here we go. Not bad, but not good either. Now let's go ahead with L'Hopital's rule. Take the derivative of the numerator. We have 30x minus 1. How about the denominator? We get 24x minus 26. Those are both easy computations. And then plug in the numbers and do your computation with the help of calculator. Now, which is easier? This time, definitely L'Hopital's rule was easier, isn't it? I mean, this computation, well, it looks like one-liner, but the factorization here for both numerator and denominator, those are rather tough because they are both non-monic. But if you use L'Hopital's rule, it is truly one-liner. Here's a warning though. L'Hopital's rule, oh, excuse me, I didn't mean to completely kill it off. Okay, let's suppose we have this kind of problem, but okay, all right, let me change the problem. Now, this is no longer 0 over 0 type limit. If you plug in x equal to -1, you see. So this is actually a trivial limit. So how do you actually calculate out? Well, just plug in x equal to -1. Plug in x equal to -1. Plug in x equal to -1 here. If I do that, what do you get? Let's see. The numerator is 2 minus 8, so -6. And the denominator is 1 plus 3 plus 2. 1. Yeah. Looks like that's what I'm getting. Is that really the case? Yes, -1 is correct. Now, what if I try to force L'Hopital's problem? I mean, what if I try to force L'Hopital's rule here? Then this is what I'm going to get. Take the derivative of the numerator, which is 4x, and then down here, I'm going to get 2x minus 3. So if I plug in x equals to -1 now, I'm going to get something different. And this is, let's see, -4 over -2 minus 2, so -5. So this is 4/5. Something different. This is wrong answer. What just happened? L'Hopital's rule applies for 0 over 0 type limit. This limit is not a 0 over 0 type limit. It's a trivial limit. So whenever you're applying L'Hopital's rule, make sure you plug in the numbers, and indeed, if it is 0 over 0 type limit, check. Check it first before applying L'Hopital's rule. Sometimes you may end up with some trivial limit, which is supposed to be a giveaway problem, but somehow you apply L'Hopital's rule and end up with 0 credit. That happens. Okay, let's go to the next problem here. If you're going to use factorization method, oh boy, it's this complicated. I think I warned you before in lesson 2, right? I mean, here's a method, yeah, but we're going to learn easier method later. That's what I said, I think. Indeed, let's apply L'Hopital's rule. Oh, wrong key. Let's apply L'Hopital's rule. The derivative of denominator is easy, it's just 1. And how about the numerator? We'll have to apply chain rule. 1/2 comes out because this is actually 1/2 power. And subtracting 1 from the power, we get -1/2 power. You have to multiply the derivative of the inside here, but that's just 1, so you don't really have to multiply. Okay, all done. Plug in h equals to 0. What do you get? We have 1/2. You see, this is truly one-liner. The derivative computation applied chain rule, but not too bad otherwise. Compare that with this method. L'Hopital's rule clearly wins. Now let's go to the last problem here, D. This time, you cannot apply factorization at all because, well, we have transcendental function here. So we cannot apply any kind of algebra here. No factorization, nothing possible. But if you plug in x equal to 0, then you're going to get, well, e to the 0 power is 1, so the numerator is 1 minus 1. You're going to get 0 over 0 type limit. So, how do you apply that? Well, no sweat, L'Hopital's rule, take the derivative, and we get e to the x over 1. Okay, alright, that's not a 0 over 0 type limit, so plug in the numbers and do your computation. You get 1. Alright, we went through 0 over 0 type limit. Now, how about infinity over infinity type limits? I don't think we have time to complete it. We're going to talk about the examples that work. And then we're going to talk about examples that will not work in a separate video. Okay, alright. Here's an example that works. We have polynomial over polynomial, a rational function. In that case, much easier method is to use asymptotic estimation. Just take the highest degree terms only, throw away the rest, and then do your computation. It's 2 over 1. Now, will L'Hopital's rule improve this computation? Actually, it does not. It works, but it does not improve this computation. Take the derivative, so we have 4x over 2x minus 3. But then again, that 2 is infinity over infinity type limit. So let's take the derivatives again. 4 over 2. Okay, that works, and we get the same answer as before. So which do you prefer? Me, I prefer asymptotic estimation infinitely more. Number 1, because this always works. That's the biggest reason. Number 2, it's simple. By itself, it's simple. Now, how's L'Hopital's rule? It does not always work. That's the biggest problem. When it works, it's not too bad, as you can see, but it does not always work. How about the next example here? Well, okay, all right. Asymptotic estimation is going to be a challenge because of all those radicals. But then again, we went through this already in lesson 2, so let me go ahead with this very, very quickly. Well, we take the leading term inside the radical and outside the radical, do the same thing in the denominator. Disregard the rest. And then we have simplified version here. 2 different functions, but they share the same limit. Okay, let's take this x to the 4th power out. And as for the second radical here, we have 3x, but that's just first order, so this is unnecessary. That part just goes away. So what's left is this expression, and then cross out all those x squared. That's what you get, and indeed, square root of 2 minus 1. We went through this very same example before. Tricky, but this is not too bad, and also this is proper way to handle it. Now, what if you apply L'Hopital's rule? You're going to get a mess. Apply the chain rule, multiply, and then subtract 1 from the power, and chain rule says multiply the derivative of the inside. The radical did not disappear. It went to negative 1/2 power, and oh boy, this is a huge mess. Clearly, it got worse than before. So L'Hopital's rule failed. Theoretically, it should work because we have 2 identical limits, actually. This limit and that limit have the same value. Yes, theoretically, yes, that's true. But this limit is even worse than this limit. So you cannot actually do any computation with it. That's how L'Hopital's rule is failing for infinity over infinity type limits, especially when you have radicals.